draw a tangent line at some point. Let's say at this point, there is a tangent line here, right? So local linear approximation basically says that if I keep myself closer to this point, if I don't go, let's say in this vicinity, right? So see, there is a very, these blue line and the black line are very close to each other. If I go a little far here, you see the distance is too much in the black line and the blue line. Similarly here, there is a distance. But close to here, they are very, in this red circle, you see, blue and black lines are very close. So basically, you remember that when we have y is equal to f of x, then y minus y naught is equal to m tan x minus x naught is the equation of tangent line, right? This tangent line has this equation. So I can write y is equal to y naught plus, if I send this y naught here, y naught plus m tan x minus x naught. But here you see y naught is the function value at x naught, because this is my this point is x naught and this is y naught, right? So y naught comes from the function f at x naught. So I just replace the value plus m10. You know that the slope of the tangent line comes from the derivative at x naught, x minus x naught. So this is the equation. This is the function on the right hand side. It's a function of x, you see, because x is a variable here. This x is a variable. So y is equal to, this one is the equation of blue line, and y is equal to fx is the equation of this black line, right? What we are claiming that if my other x, if I pick any x here within this interval, within this circle, you see, within this circle, if I pick any x here in this interval, if I pick any x, means if x is close to x naught, right? Close to x naught, then my function which comes from the black line, which is f of x, and a function that comes from the blue line, which is fx naught plus f prime x naught, x minus x naught. This is coming from here, right? And this is coming from here. These two are approximately equal. Okay, this is called local linear approximation. The function on the right hand side is a linear function because it's a straight line. And the function on the left is any function which may not be linear, right? It is any function. And this is a linear function which comes from the straight line coming from the same fx. So they are equal. So we are approximating a function by a linear function. That's why we call it linear approximation. And why we call it local? Because whenever we are closed, we are not going, you know, if you live in Bremi, right? So we will say that you are local from here, right? And if you are coming from outside, maybe Sohar or Baskat, you are not local from here. So local means when you live in the vicinity, in close by here, right? So when x is close to x naught in local neighborhood, then it is the case. So we can also write, because x minus x naught is the distance of x from x naught, if we call it delta x, if we let x minus x naught let delta x, where delta x is small, right? Because when x is very close to your x naught, then this delta x will be small. We can write the above equation as f of x becomes x naught plus delta x, approximately equal to f of x naught plus f prime x naught, and x minus x naught is delta x. So we can write like this as well. These both are the same. This is also called local linear approximation, but here delta x has to be small. So if you see here, these are two things written here, this one and this one. So this is called local linear approximation of f at x naught. So if I write local linear approximation of the function f at the value x naught, if I change x naught, the approximation will change. Means if I take some other x naught here, right? So at every point, if I keep on changing x naught, if I take x naught here, then my tangent will be like this. If I take x naught here, my tangent will be like this. So at every point, I can define a different local linear approximation. Okay. So see the first example here. I can record, right? Okay, so someone is recording already. That's good. It's being recorded, right? Yes, okay, that's good. So if you look at this one, find the local linear approximation of fx equal to square root of x and x naught is 1, right? So see example 1 on page 212. Example 1 on page 212. So my fx is square root of x and x naught is 1. So what do I need? First of all, I need the derivative f prime of x, which is because it is x to the power 1 by 2. So it will become x to the power 1 by 2 minus 1 by 2. So this will become 1 over 2 square root of x. Now, at these 2 points, I should calculate f of x naught. X naught is 1. So f of 1 is square root of 1, which is 1. And f prime at x naught is f prime at 1, which is 1 over 2 square root of 1. So that is 1 by 2. So I got these two values. So therefore, the local linear approximation for square root of x will become, so therefore, fx is approximated by fx naught plus f prime x naught x minus x naught. So I can replace the values. Square root of function is square root of x, approximately equal to f of x naught. I calculated it 1 plus f prime is 1 by 2 and x minus x naught is 1. So you can simplify the right hand side. It will become 1 plus half x minus half. So it will become half plus half x. So this is what you got, right? Half plus half x. So if you simplify this, so that is the local linear approximation. Then he said, use the local linear approximation to approximate 1.1, right? So I can just replace 1.1 now. So he said, use this to approximate square root of 1.1. So 1.1 is equal to 1 plus 1 by 2. X is 1.1 minus 1. So see, I replace this x by 1.1. You see, that means because whatever x you have here, that x goes here. Every other thing is fixed. So if I replace x by 1.1, only this 1.1 will be changed. Or you can put it here, half plus half into 1.1. Both will give you the same answer. So this will become 1 plus 1.1 by 2 is 0.55 minus 1 half. It will become, this is 0.1. So 0.1 by 2 is 0.05. So it is 1.05. So if you use calculator and find this square root of 1.1, square root of 1.1 from calculator is 1.0488, 1.049. So see, very, very close, right? So see, it's a very good approximation. From calculator, square root of 1.1 is equal to 0.4888, right? So that is approximately, sorry, 0.0. 1.0488, right? So this is 1.09, 1 point, almost 1.5, right? 0.149. So see, very, very close to each other. So it's a good approximation, right? Good approximation. See, this is from calculator. This is what we obtained from calculator. So of course you can say that when we have calculators, why we are doing like that? But we are just saying that a function can be approximated by its tangent line if your x is very, very close to x naught. And sometimes in mathematical calculations, we need to approximate our function. So at that point, we cannot use calculator. So we have to use this square root of function like this. So see, if I draw square root of x function is this one. This is square root of x, right? And if I say this half at x prime equal to 1, if I draw a tangent line, this is 1/2. So this is the tangent line half plus half x, right? So this is the other function. If I keep myself close to this 1, then my approximation will remain very good. But if I go very far, let's say at 2, if I calculate this at 2, it will not be a good approximation. You see, uh, at 2, square root of 2 is equal to half, 1 plus half, 2 minus 1. So that is 2 minus 1 is 1. So 1 plus 1/2 is 1.5. But from calculator, if you calculate square root of 2, it will be 1 point square root of 2 square root of 2 is 1.41. So now you see you are very far. 1.41 is far from 1.5, right? So it's not a very good approximation when you took x is equal to 2, right? Because x is not close. Here 1.1 was close. Good approximation because 1.1 is close to 1, right? So see here, they did not ask me, but I just tried to show you that why this is a good approximation. So this is not very close, right? Not a good approximation. 1.5, not a good approximation. I will not say very bad approximation, but we can say that it's not a good approximation. Still 1.41 is close to 1.5, but not that close, which we want, right? So something happened here. 1 plus 1 by 2, 1.5. So not a good approximation. And what is the reason? Because 2 is not close to 1, right? So at 1.1, 1.2, maybe 0.9, 0.8, they will give you good approximation. So what is the third case here? Yeah, only 2 parts. So we are done here. So see here, this is the exact graph. So see, as we are close to this one, you see these two lines are very, very close. The blue curve and this one, they are very close to each other. See, almost equal. But as I go little far, you see, then there is a distance. Then these approximations are not good. This is another example which is given for sine x. So see, from almost this point to this point, you see, the approximation is very good. Red and blue lines are very, very close to each other. So you can see this example as well. Then we can define differentials. Differentials can also be defined to approximate things. Okay. There are two things. One is the change in f and one is the differential in x. So what is a differential? You see, when y is a function of x, then the derivative of y with respect to x is f prime of x. This is what we call, right? If we pretend that this dy, basically this dy by dx is one thing. It's a derivative of y, right? It's one thing, which is derivative of y with respect to x. But if we treat dy and dx as separate quantities, which are basically called differentials of y and differential of x, if we treat them as separate quantities, then we can write dy as f prime x dx. Then I can multiply this denominator here on the right side. Agree? Because if we treat them separate things. So these are differentials of x. So this is called a differential of y, dy. Okay, and dx is the differential of x. So these are two things. If x is your independent variable and you add something in it and come to this point, let's say if this is x and you added some small number in it, x plus delta x, you came here. So this distance is delta x, right? So this delta x is basically change in x, which is the same as dx as well, differential of x. So independent variable, for independent variable, x is independent variable. For independent variable, change in x and differential in x, they are the same. But if you calculate the corresponding change in y, this is y, and this is the change in y. Okay, so let's say this is the corresponding change delta y. So this point is y plus delta y. So delta y is change in y, which we calculate by function value at x plus delta x minus the function value at x. This is actually the change, actual change in y. This is not equal to differential of y in general. Dy and delta y are not equal in general. Okay, but if delta x is small, then your change in delta y can be approximated by the differential of y. Change in y, actual change in y is this, right? Actual delta y is this, f of x plus delta x minus fx, right? But dy is f prime x dx, right? Again, from the local linear approximation, f prime x dx. So the change can be approximated by your differential. So see, if I go back here, if I bring this to the left, it is fx minus fx naught, which is this one. So this is differential of x. You see here, f prime x, this one is differential of x dy. And if I bring it here, f of x plus delta x minus f of x is change in x, which is delta. So this will give you delta of y, and this give you d of y, right? So delta y and dy approximate each other. They are not equal. So this is what basically we did here. Okay, so let's not write it here because otherwise it will be confusing for you. So I can erase it, because when you will see notes, then you don't know what is dy and delta y. So maybe we can just write it here. So we can use differentials to approximate things as well. For example, in previous example, exact change was approximated by differential, right? Exact change delta y was square root of 1.1 minus square root of 1. That was the exact change, which was 0.0488, or you can say 0.049, right? But what we calculated dy, which was f prime x naught into delta x. That was 1/2 into 0.1, and that was 0.05, right? So see, delta y and dy are approximately equal to each other. Why? Because delta x, this was delta x, because delta x is small. So when delta x is small, they are approximately equal. They are both approximately 0.05. So what we did here on the right, in this example, what we did here, this one basically was dy that we calculated. Okay. So see here, for the same question, he said find the formula for delta y and dy. So we can do that. And then by taking different values, we can approximate these things. So if I go to the exercise, you will see here. Here he said use that local linear approximation that we did in the example one, but in uh, here he said use differential dy to approximate delta y when x changes as indicated, right? So see if I do this problem 51 on page 218. Exercise 51, page 218. Your fx is given. Y is square root of 3x minus 2. And he said x changes from 2 to 2.03. X changes from 2 to 2.03. So see here, x changes from 2. So I will take 2 as x naught because you see x was 2 and now it has become 2.03. So the distance between these two is 0.03. So that is my delta x, 0.03. And we take the first value as x naught, remember. So we take this 2 as x naught because it started from 2. So x naught is 2 and this is your delta x. Now, so delta x and dx are the same as I told you. Delta x, dx are the same. He said approximate delta y using differential, using dy. So we know that dy is the derivative of this thing. If this is my fx, the right hand side is fx. So this is f prime x naught into delta x. So first of all, I need f prime x naught here. So what is my f prime x or dy by dx? You can say whatever. F prime x will be 1 over 2 square root of 3x minus 2, and the derivative of 3x minus 2 is 3. So I will calculate f prime at x naught, which is 2, right? X naught is 2, f prime at 2 into delta x, which is 0.3. So what is f prime at 2? It is 3 over 2, and 3 to the 6 minus 2 is 4. So 4 is also 2, so that is 3 by 4. So this is 3 by 4 into 0.03. So that is your answer. So if you use calculator, so this is 3 multiplied by 0.03 divided by 4. So this becomes 0.0225. So this is the approximate change. This is approximate change in y because x changes from 2 to 2.3. So there will be some corresponding change in your y. You see, this is first y, so your y will become this one. So you can, so this is the change basically, that is delta y. Okay, this is delta y, but we are not calculating the actual change. Actual change will be different. But he said use differentials to calculate the actual change. If you want actual change, which is not the part of the question, but I'm just telling you that actual change is function value at 2.03 minus the function value at 2. Because x changes from 2 to 2.03, so we will calculate this. So the function value at this is 3 into x 3x minus 2 and minus function value at 2. So if you calculate, this is the actual change, and you can see that it will be very close to 2 point, very close to this number. So you can calculate this actual changes. Here he said use the local linear approximation to estimate this 3.02 to the power 4. Exercise 23. Right? And what is the page number? 218. Page 218. So he said approximate this. From calculator, of course, I can very easily find that. Right? But let's see. Calculator gives you 2.02 to the power 4. 3.02 power 4. So that is 83 point. From calculator, the answer is 83.1817 almost, right? So let's see. Let's see how close we get using the local linear approximation. First of all, he did not give me anything, no function, nothing, right? So what I can do, I can let my function be x to the power 4, right? And what is the closest value to this 3.02? Closest value to 3.02 is 3, right? So what I need, and I need f of 3.02. This is what I want, right? So it means what is the difference? My x naught is 3, but actually I want the value at 3.02. So it means there is a difference of 0.02, which is delta x. Okay, so anyway, what we can do, we can write the local linear approximation like that. My local linear approximation was fx approximately, or I can find first these two values, fx naught, which is f of 3, that is 3 to the power 4, and that is 81. We all know that 3 to the power 4 is 81. This is fx. Now I need the derivative at x naught. So derivative at 3, derivative is 4x cube. X is 3. So 3 to the power 9 is 27, and 27 into 4 is 108. Now, therefore, my fx is approximately equal to fx naught plus f prime x naught into x minus x naught, right? So that is, so fx is x to the power 4 approximately equal to fx naught, which is 81, plus f prime, which is 108, and x minus 3. So this is my local linear approximation. Now, what was the question? Question was this 3.02 to the power 4. So now I will calculate this at x equal to 3.02, right? So this will give me 3.02 to the power 4 approximately equal to 81 plus 108, and x becomes 3.02 minus 3. So this is what I have to calculate, and this should be equal to this number 83.1817. So let's see. This is 0.02. So multiply 108 by 0.02. So this will become 2 plus 81. So that will give me 83.16. See what we had, 83.18. 3.02 power 4 was, yes, 83.18, and this is 83.16, right? So again, you see, good approximation, because exact answer was this one. This is the exact answer, right? Using calculator. So again, the question is not that when we have calculator, then why we need all this practice to do this one. Here we are doing this practice just to motivate ourselves that this approximation is very good, this local linear approximation. Sometimes when we are dealing with mathematical formulations in our mathematical modeling, sometimes we cannot keep our function. We have to simplify our things. We replace our function by the local linear approximation because linear functions are easy to use, right? So over there, because we know that this local linear approximation is a good approximation, so without thinking anything, we replace our function by linear functions, which are obtained from this right hand side. So our aim is not to calculate 3.02 to the power 4. Our aim is later on when we need something like that in our projects or somewhere else, we can easily use that. I don't know that whether in calculus 1 they did 3.6 or not. L'Hopital rule to find the uh, limits. When I taught calculus 1 year back, I think in fall of previous year, I taught that, but I don't know about Dr. Badriya, whether she did it or not. But it's very simple application of derivative. That's why it is here. It is L'Hopital's rule. Basically, we pronounce it as LO, low, and Pital rule, L'Hopital. We don't call it L'Hopital. LHO is low from here to here. It is like low, and then we call Pital, L'Hopital rule. Okay, so it's not an English word. It looks like L'Hopital, right? So we read as this L'Hopital rule. Even if you say L'Hopital rule doesn't matter because it sounds like L'Hopital, and because it's not from our language, so we can do anything with that, right? Anyway, what is L'Hopital rule? Sometimes when you take the limit of some functions, x goes to a number, we all remember the limits, right? And when we have the quotient of two functions, sometimes what happens when we replace the limit, it gives me either 0 by 0 form or infinity by infinity form. These are called indeterminate forms. Indeterminate forms. Because if something is 0 by 0, I don't know what is the answer. 0 by 0 is not 1. You remember when you divide 0 by 0, you can say that 0, 1 is 0. So if I subtract, nothing is left. So the answer is 1. But someone can say that, okay, if I multiply 0 with 10, the answer is still 0. And if I subtract, nothing is left, right? So again, my answer should be 10 as well. So that's why we call them indeterminate forms, because we don't know what is the answer. Someone can say that it is 1, someone can say that it is 10. Or you see, if there is any number divided by 0, it gives you infinity. But if 0 is divided by any number, it gives you 0. So again, there is a fight. When 0 is divided by 0, should we go with this 0 and call it 0, or should we go with this 0 and call it infinity? Right? So again, we don't know what should be the answer, right? So that's the reason we call them indeterminate form. So when this type of thing happen, L'Hopital rule says that you can replace this limit by another limit where f is replaced by the derivative of f and g is replaced by the derivative of g. Okay. So this is basically L'Hopital rule. So for example, if you see, if you have limit x goes to 0, sine x divided by x. Now you see, if you just replace x is equal to 0, sine 0 is 0 and x is also 0. So you see, this is 0 by 0 form. It means I can use L'Hopital rule, L'Hopital rule. So what is L'Hopital rule? L'Hopital rule says that replace sine x by its derivative, which is cos x, and replace x by its derivative, which is 1. So see what we did? We replace this x by its derivative cos x, and we replace Sin x by cos x and x by 1 by their separate derivatives. Okay, so d by dx, the derivative, not the derivative of the whole thing. We did not replace the whole derivative f by g. Okay, remember, is it not true? We replace f by its derivative, g by its derivative. Otherwise, we know that if I replace f by g by its derivative, it uses the quotient rule. It is f prime g minus f g prime divided by g square. That is the quotient rule. We are not using it. Okay, we are not using this one. Okay, we are not using the quotient rule. We are replacing the derivatives of f and g by their own derivatives. And now if I replace, so this is, we can say that we use L'Hopital rule or L'Hopital rule. Okay, so we use L'Hopital rule and we wrote that. Now if you put the limit cos 0 is 1 and divided by 0 is 1. So see, your answer came out to be 1. Not 10, not 0, not infinity, not any other number. Another example, you can see limit x goes to 0, 1 minus cosine x by x. This is also 0 by 0 form. You see, if I put cos 0, cosine 0 is 1. So 1 minus 1 is 0 divided by 0. Again, 0 by 0 form. So what I can do, I can use the L'Hopital rule. The derivative of the whole thing here is 0 plus sine x, and divided by the derivative of x is 1. So that is sine x by 1. And now if you take the limit, it is not 0 by 0 form, it is 0 by 1. So sine x will become 0 divided by 1. So your answer is 0, not 0 by 0. So this answer is 0 by 1 is 0. It is not in indeterminate form anymore. 0 by 1 is not indeterminate. Now it is 0. So the answer is 0 here. So we can perform this thing for different rules, you know. So see all these examples, you can see they all use L'Hopital rule, very simple. Take the derivative up and down, replace, you see here, we replaced sine 2x by its derivative, x by its derivative. So you can directly, if you have a practice, you can directly write this. Okay, but it's first time, so he's replacing before that derivative of sine 2x, which is 2 cos 2x, and then the derivative of x, which is 1. So now if you replace the values, you got the answer. Before that, it was 0 by 0 form. Sine 0 is 0 divided by x 0. It was 0 by 0, but once I use the L'Hopital rule, the answer is 2. So very simple, very straightforward rule. It is also used for infinity by infinity form. And there are other indeterminate forms as well. We can use it for that as well. But first we have to convert. You see, there is another form which is 0 into infinity form. This is also another indeterminate form. When, you know, when anything is multiplied by 0 into any number, it makes it 0. But when any number multiplies by infinity, it becomes infinity. So again, you see, we have a problem. If we multiply 0 with infinity, then what should be the answer? We don't know. So this is also called indeterminate. But there is no L'Hopital rule for this form. Like if I take limit x goes to 0, x into log of x. You know that x goes to 0, but log of 0 is infinity, right? So this is 0 into infinity form. But I do not have any rule for that. So I have to convert this. I have to convert this to either 0 by 0 or infinity by infinity form. So if I bring 1 over x down, let's say, if I keep log of x at the top, and if write x in the bottom, I can write 1 over x, right? X in the denominator becomes 1 over x. Now if you put 0, log of 0 is infinity, And if you put 0, 1 over 0 is also infinity. So see, this has become infinity by infinity form. Now I can use L'Hopital rule. So L'Hopital rule says that take the derivative of log of x. So the derivative of log of x is 1 over x, and divided by the derivative of 1 over x is uh, minus 1 over x square. So now if I simplify, limit x goes to 0, 1 over x into minus x square by 1. Because if I bring this up now, it will become x square by 1. And now 1x is cancelled with a square, right? So this x is cancelled with the power. So you are left with limit x goes to 0 in minus x only. Now, if x goes to 0, the answer is 0. So before that, I did not know what should be the answer, whether this 0 will give me 0 or this infinity will give me infinity or something in between. So because we were not sure, so we change it to infinity by infinity form and did it. So this is done here, you see, a part. Answer is 0. Another form is infinity minus infinity. Why this is another form? Because infinity plus infinity is not a problem. If you add infinity in infinity, it is definitely infinity, no issues. This is not an indeterminate form. But when we subtract, now these two infinities can be different than each other. I don't know. Infinity is a very large number, but they may be same, they may be different. If they are same, maybe they give you 0 as an answer. If they are not same, they may give you some number. If one infinity is twice this infinity, then answer may remain infinity. So we do not know what should be the answer. So again, we manipulate and convert to 0 by 0 form or infinity by infinity form. So again, we convert this to this one and then use the L'Hopital rule. I think the example was 1 over x and 1 over sine x. So if you take the uh, limit x goes to 0 plus 1 over x minus 1 over sine x. So now see, this is infinity. 1 over x is infinity minus 1 over sine 0 is also infinity. So this is 1 over infinity minus infinity form, right? So I have to do something with that. So if we have to take the LCM here now. If I take the LCM, it will become x into sine x. Sine x will multiply here, sine x and minus x will multiply here. Now you see it becomes 0 by 0 form just by taking the LCM. So once it becomes 0 by 0 form, I can use L'Hopital rule.
Actually, I'm going to go further.
Okay.
Yeah.
So now if you take the derivative, I have to take the derivative of this whole thing. So this derivative will become sine x is cosine minus x is 1 divided by the derivative of x sine x. Now this will use product rule, right? Remember f g prime. We did it in chapter 2. F prime g plus f g prime, because it is one function in the denominator. So x, the derivative of x is 1, sine x as it is, plus x as it is, the derivative of sine is cosine x. So this is using L'Hopital rule by L'Hospital's rule. So we use L'Hopital rule. Now see what is the answer. Now if I take the limit, it is cos 0 is 1. So 1 minus 1 is 0 and sine 0. So it is still 0 by 0 form. It is still 0 by 0 form. If it is still 0 by 0, I can use L'Hopital rule again. no issues. Okay, so here I am using L'Hopital rule again. No problem. I can use as many times as possible. Okay, so we are using L'Hopital rule again. So now the derivative of this cosine x will become minus sine x, and minus 1 is 0, divided by sine x becomes cos x, plus x cos x, again use the product rule. So 1 into cos x and plus x into cos is minus sine x. Okay, so now if you put the limits, let's say now what you get. So if you put sine 0, it is 0, divided by cos 0 is 1, plus cos 0 is 1, minus x 0 is 0. Now it is not 0 by 0 form. It is 0 by 2. So 0 by 2 is not an indeterminate form. 0 by 2 is 0. So see here, I need to use the L'Hopital rule 2 times. Okay, so from here to here, I used L'Hopital rule, right? And again, from here to here, I again use L'Hopital rule. The reason is when I use L'Hopital rule once, it again gave me the 0 by 0 form. So I can again use the L'Hopital rule. You can use as many times as possible, no issues. All right, so I think this is okay. One more rule I can do this example 6. Another rule is when you take 0 to the power infinity, 1 to the power no 0 to the power 0, 1 to the power infinity, and 0 to the infinity to the power 0. I think infinity to the power 0. So these are also indeterminate forms, because when anything has power 0, the answer is 1. So what if 0 has power 0? And when 0 has any power, the answer is 0. This is the issue. So again, when 0 has the power 0, I don't know what will happen. When 1 takes any power, 10, 20, it remains 1. 1 to the power 1000 remains 1. So we don't know once it gets to infinity, whether it will remain 1 or not. We don't know. Right? So that's why all these forms are also in indeterminate form. For these, we take log. First, we take logarithm, bring the power down. Take log and bring power down. What do we mean by that? Because there is, you remember, there is a property of logarithm that if you have any power and you take the log, this power comes down. So it becomes p into log of x. Okay, then it will become bring power down. So it means we will have 0 into infinity form. We will have this one. So we know that when we have 0 into infinity form, we convert this to 0 by 0 or infinity by infinity, because we know how to handle 0 into infinity form. So let's say an example was given. Limit 1 plus sine x to the power 1 over x, right? 1 plus sine x. So this is x goes to 0. So if x goes to 0, sine x becomes 0. So you got 1, and 1 over 0 is infinity. So see, this is 1 power infinity form. So what I will do, I will say that let y is equal to my function, because I have to take the log, and log cannot be taken on one side. So I call this as my y. Then what is the question? Then my question is, what is limit x goes to 0 of y? This is my question, right? Because this is y. So what is the limit of y? So first I will take log on both sides, log of 1 plus sine x. This is the last example. I will stop after that. And here now I can bring this power down before logarithm. So this will become 1 over x log of 1 plus sine x. Now you see it is infinity into 0, because 1 over 0 is infinity. Now if I take the limit, as x goes to 0, so it becomes limit x goes to 0 log of y is equal to limit x goes to 0, 1 over x, 1 plus sine x, right? So this is now infinity, 1 over x is infinity into 1 plus sine x is 1. So again, no, it is log. So log of 1 is 0. So infinity into 0 form. But it is automatically infinity a 0 by 0 form as well, because this is log of 1 plus sine x, which is 0, divided by x is 0. So see, I can write 1 over x as in the denominator. So this is 0 by 0 form. If it is 0 by 0 form, then I can use L'Hopital rule. Limit x goes to 0. Log of 1 over sine x is 1 plus 1 over sine x into the derivative of the denominator is cos x, divided by the derivative of x is 1. So this becomes limit x goes to 0. Now it has become cos x over 1 plus sine x. Now I think you can use the limit. So here I used L'Hopital rule. So wherever I use L'Hopital rule, I can just write that we used L'Hopital rule. So cos 0 is 1 divided by 1 plus sine 0 is 0. So see, the answer is 1 here. But this answer is log of limit x goes to 0 y. You see why this is the case? Because limit comes out of the logarithm, or you can take that limit can go inside the logarithm. So we can write the log outside and bring the limit inside. What was my question? My question was, what is limit of y without the logarithm, without this logarithm, right? So what I can do, I can send the logarithm on the other side. So limit x goes to 0, y becomes, when log goes to the other side, it becomes exponential. You remember? When log of y is x, then y becomes, log becomes exponential, e to the power x. So because the answer is 1, so I will get e to the power 1 here. So when log goes there, it becomes exponential. Okay, so that's why it is e to the power 1. So my answer is e. You see, at the beginning, I did not know what should that be. 1 to the power infinity, but it has become e. E is 2.7183, right? You don't have to write that 828 so on. This is your e. But see that it is not 1, not infinity. It has become 2.7183. You see, if you take any power, 100,000 billion, it remains 1. See, but once it has become infinity, we don't know what should be the answer. So we are not saying that whenever we have 1 to the power infinity, it will be 2.7183. No, we are not saying that. Okay, we will have to see what the answer is. In this question, the answer has become E, which is 2.718. Okay, so this was these two were again the applications of the derivatives. So that's why we went through that. So 2.2, 2.3, 2.4, 2.5, 2.6. These are all techniques of derivatives, differentiation. How to take derivatives of different functions, and 3.1, 3.2, 3.3 as well. Okay, and then 3.4, 3.5, 3.6. We did these as applications. Okay. So chapter 4 is also application. So we will continue with chapter 4 in next lecture. Okay, so next lecture. All right, so that's it from my side. Now, if you have any questions, you can let me know. Otherwise, we can stop. So I hope this will help you. Go through that and try to do the problems that I gave you in the assignment as well. Finish it as soon as possible so that if you have any questions, we can answer. I'm stopping the recording now. So I think 2 more students come, Sarah, Aisha, Halima, Imad, and Allah. All right, so I will put your present as well. So see you on next week, inshallah, and try to finish faster.